This is Srikanth S, Assistant Professor of Triple Department. In this session, I am going to explain about torque equation and torque speed characteristics of induction motor. The torque equation of induction motor can be derived from the basic principles of electromagnetism and the operation of the motor. Here is the simplified derivation. The first point which we need to consider for generating the torque is the magnetic field interaction. As we know, always induction motor operates on the principle of electromagnetic induction. The stator of motor produces rotating magnetic field when supplied with a three-phase AC current. This is our main magnetic flux, that is rotating magnetic flux, which is developed in the stator winding. And the second point is rotor induction. The rotating magnetic field induces a voltage in the rotor windings. According to Faraday's laws of electromagnetic induction, a voltage is induced in a conductor when it cuts the magnetic flux lines. This induced voltage in the rotor causes rotor currents. And the next, how the torque is developed. Rotor currents and torque. Rotor currents interact with the magnetic field which is producing a torque. The torque is essential for the motor to overcome the mechanical load, because the motor has to generate a mechanical energy. So the mechanical energy is done with the development of the torque. Once the torque is developed, the rotor starts rotating. The twisting force in the induction motor will start, so that the twisting force will make the rotor to rotate. This is the way we are going to get the torque in the induction motor, with the interaction of magnetic field and the conductors. Here the developed torque in an induction motor can be expressed by the following simplified equation, where torque is equals to K into S into Vs into Is, where K is a constant, S is the slip of the motor, which is the relative speed difference between the rotating magnetic field and the rotor. S is nothing but the slip. It is the relative speed difference between the rotating magnetic field and the rotor, where Vs is the stator phase voltage and Is is the stator current. Here electrical power is equals to 3 into 3 Vi cos phi. Here the stator currents which we are taking, 3 into E2s into I2s into cos phi 2s. Here 3 into E2s into E2s by I2s is nothing but E2s by Z2s. I2 is nothing but voltage by impedance. So E2s by Z2s, which is multiplied with cos phi 2s. Cos phi 2s is nothing but, in the impedance triangle, cos phi is equals to R by Z. That is equals to R2 by Z2s, which is equals to 3 into E2s square into R2 by Z2s square. Here Z2 is nothing but, we are going to have R2 square plus Sx2 square. So 3 into S square into E2 square into R2 by R2 square plus Sx2 whole square. This is the electrical power which is developed, where power input to the rotor is equals to 2 pi ns into Td. 2 pi ns into Td. So here S into rotor input is equals to rotor copper loss. S into rotor input is equals to rotor copper loss. So S into 2 pi ns into Td, which is equals to whatever the rotor copper loss, 3 into S square E2 square R2 by R2 square plus SX2 whole square, which is equals to Td is equals to 3 into E2 square by 2 pi ns into SR2 by R2 square plus SX2 whole square. Here Td is equals to K into S into E2 square, S into E2 square by R2 square plus Sx2 whole square, in which is multiplied with the rotor resistance R2. Here, this is the developed torque equation in the three-phase induction motors. In this, to draw the torque speed characteristics of an induction motor, first we need to check how the motor torque varies with its speed of rotation. These characteristics are crucial for understanding the motor's behavior under different operating conditions. The typical torque speed characteristics curve of an induction motor is commonly divided into three regions. One is the starting region, that is region 1. At this region, at the start, the motor is stationary and the slip is the difference between the synchronous speed and rotor speed is maximum. So the starting torque is also maximum. So motor draws high starting torque during this period. Here when S value is maximum, that is nothing but let us consider S value is 1, torque is equals to K into E2 square into R2 by R2 square plus X2 square. So this is the starting torque equation. This is the starting torque equation. This torque is available at the starting of the motor. And the next one is the acceleration region. This is also called as region 2. As the motor accelerates, the slip decreases, slip value decreases, and the torque gradually decreases. The acceleration region is characterized by decreasing torque with increasing speed. So the motor operates in this region until it reaches a stable speed, which is known as the synchronous speed. And the third one, synchronous speed region. The synchronous speed region, at synchronous speed, the slip becomes 0 and the motor operates with the minimum torque required to overcome the friction and windage losses. The torque at synchronous speed is referred to as the pull-out or pull-up torque. This is the torque which is called as pull-out or pull-up torque. And the next one is the pull-out torque. It is the maximum torque that the motor can produce without stalling. Beyond the pull-out torque, the motor enters the breakdown region and the torque decreases rapidly until the motor stalls. The maximum torque before stalling is called the breakdown torque. It is important to note that shape of the torque speed curve depends on various factors including motor design, loading conditions, and the type of rotor, the torque speed characteristics, which can be affected by the rotor resistance and rotor reactance and other parameters. It is the torque speed curve is going to depends on various factors which is having different load conditions and different uh, type of rotors we have used, and what is the rotor resistance, what is the rotor reactance, like that several points are there in order to get the torque speed characteristics. Now let us go with the torque speed characteristics. The torque speed characteristic curve is essential for selecting and operating induction motors in various applications, because the whenever for any machine, when we are having what is the torque condition, what is the speed condition, at which speed we are getting the maximum torque, like that if we have the complete data, so that we can easily use for different applications. So whenever there is a application, so we have to check the characteristics. Based on the characteristics, we can we can choose the motor with different speed conditions and torque conditions, and it helps determine whether a motor is suitable for a specific load and provides insights into the motor's performance under different conditions. So here it also specifies that what is the load condition and also the performance of the motor under different conditions. So based on our requirement, we can choose the motor. And engineers use these characteristics to ensure that the motor operates reliably and efficiently in a given application. Here, this is the torque speed characteristics. Here the torque is in this particular direction. The torque is in this particular direction. And here this is the slip, and here the motor speed is 0. Here the motor speed is 0, and here the motor speed is at synchronous speed. When the motor speed is at synchronous speed, the slip value is 0, and here the slip value is 1. So the here the motor speed is increasing in this particular direction, and the slip value is increasing in this particular direction, because slip is equals to ns minus nr by ns. So here the slip is increasing in this particular direction. So, and these speed torque characteristics are separated. One is with the stable region and another is the unstable region. Here in the stable region, at low values of slip, torque is equals to K into S E2 square R2 by R2 square plus SX2 whole square. So here at low values of slip, when S value is less, when S value is very less, that is 0.01, let us consider. So when S value is very less, that is during the period 0, it is when from S is equals to 0 to S is equals to Sm. During this period, the slip values are very less. When slip value is less, S square value is very less. Very less. So we can neglect this S square value. So here we are going to have the equation which is proportional to S. Torque is proportional to S. When slip increases, torque increases. This is for low values of slip. This is for low values of slip. When the slip increases, torque will increase. When the slip increases, torque will increase. This is the stable region. When low values of slip, when slip increases, torque will increase. Now let us consider the unstable region, that is when there is a high value of slip. High value of slip. When there is a high value of slip, here Sx2 value is greater than R2. Sx2 value is greater than R2. In this condition, we are going to neglect the R2 value. R2 is neglected. When R2 is neglected, our torque equation will become torque is equals to K into S into E2 square into R2 by R2 square is neglected. So S into Sx2 whole square. Sx2 S square into x2 square. Let us consider. So S and S square will get cancelled. So here T is proportional to 1 by S. So at high values of slip, torque is inversely proportional to the slip. So here after this particular point, that slip, when slip increases, torque is going to decrease. This is called unstable region. And this is the point where we are going to get the maximum torque. And at this point, whatever the slip is there, and that slip is taken as slip at maximum torque. Slip at maximum torque. And point A is maximum torque, and point B is the starting torque. That is, the speed is 0, slip is 1. So, which will be having some torque that is taken as the point B, that is starting torque. And point C is the full load torque, TFL, that is the full load torque. This is the way we are going to get the torque speed characteristics under the stable region and unstable region. And when we change the rotor resistance, so when we go on changing the rotor resistance, the maximum value of torque will never change. Only the position where we are going to get the maximum torque is going to change. The position where we are going to get the maximum torque is going to change. Here, this is SM1, SM2, SM3, SM4, that is R2 is equals to X2, which we are going to get the slip value as 1. So these are the different torque speed characteristics under various rotor resistance conditions. Now we'll go with the problems. Now let us go with a three-phase slip ring induction motor with a star connected rotor has an induced EMF of 120 volts between slip rings at standstill with normal voltage applied to the stator. The rotor winding has a resistance per phase of 0.3 ohms and standstill leakage reactance per phase of 1.5 ohms. Calculate the slip and rotor current per phase when the rotor is developing maximum torque. So here first let us write the data given, that is here the rotor induced EMF, that is E2 is equals to 120 volts, and the rotor winding has rotor resistance per phase R2 is equals to 0.3 and X2 is equals to 1.5 ohms, and we need to calculate the slip and the rotor current per phase when the rotor is developing maximum torque. Here torque is equals to K1 into S into E2 square into R2 by R2 square plus Sx2 whole square. Here the condition for maximum torque may be obtained by differentiating the above expression with respect to the slip. After differentiating the above equation, we will get the R2 is equals to Sx2. This is the condition for maximum torque. R2 is equals to Sx2. From this, S is equals to R2 by X2, where S is equals to 0.3 by 1.5, which we are going to get the slip value as 0.2. Now, after getting the slip value at maximum torque, now we need to calculate what is the impedance. What is the impedance? X2 under running condition is equals to S into X2 under standstill condition, where X2 under running condition is equals to 0.2 into 1.5, that is equals to 0.3 ohms, where ZR is equals to square root of R square plus X square, where ZR is equals to 0.3 square plus 0.3 square, where we are going to get the impedance of rotor as 0.42 ohms. After this, we need to calculate what is the rotor current. So, for calculating rotor current, we need what is the rotor voltage. And we know that for a slip S, the rotor induced EMF will be S times the induced EMF at standstill. So, ER is equals to S into E2, where ER is equals to 0.2 into 120 by root 3, which is equals to 13.86 volts. And hence the rotor current per phase will be derived as IR is equals to ER by ZR, that is equals to 13.86 by 0.42, which we are going to get it as 33 amperes. Hence, at a slip of 0.2, the rotor current per phase is 33 amperes. This is the way we have to calculate the slip at maximum torque and rotor current. And now we'll go with the next problem, that is a three-phase 460 volts. Now we'll go with the another problem, a three-phase 460 volts 100 HP 60 Hz 4-pole induction machine delivers rated output power at a slip of 0.05. Determine the rated torque. So here first we are going to take the given data, that is Vs is given as 460 volts and the frequency is given as 60 Hz and number of poles is given as 4 and slip is given as 0.05. We need to calculate what is the torque. So in order to calculate the torque, power is equals to omega m into T. That is, in order to calculate the omega m, First, let us go with the calculation of synchronous speed. Ns is equals to 120 F by P, where frequency is given and number of poles are given. So, if we substitute the frequency and number of poles into this equation, Ns is equals to 120 into 60 by 4, where we are going to get it as 1800 RPM. After getting the Ns, in order to get the motor speed is equals to Ns into 1 minus S, that is 1800 into 1 minus 0.05, which is equals to 1800 into 0.95, where we are going to get it as 1710 RPM, where P is equals to omega m into T. From this, T is equals to P by omega m. So here T is equals to P into 60 by 2 pi n. 60 by 2 pi n, where omega m is equals to 2 pi n by 60. So torque is equals to, if we substitute these values, that is number of poles as 4 into 100 into 60. Number of poles as 4 into 100 into 60 divided by 2 into 3.14 into 1710. Sorry, this is the power, not number of poles. Here it is the power. The power we have calculated is 100 HP. For 100 HP, it is multiplied with the 100 into 746 watts into 60 by 2 into 3.14 into 1710, which is equals to 416.6 Newton meters. This is the way we have to calculate the torque parameters of the given induction motor. In this session, we have discussed what is the torque equation and what are the parameters which are affecting the torque equation and speed torque characteristics, and some examples in the speed torque characteristics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.